I'm okay, how are you? What happened to you? There's a company. An accident? Oh, too bad. But you're able to see?
Yeah, I'm able to see.
Okay. Okay. And he was doing what? Thank you, sir. Thank you. All right, guys. So there's just one, I think, question that I gave you guys to go and do. It's important that we do it together. Nothing complicated about it. But then also just for me and just trying to put this on record so that people are easily referred back to. All right, so this ideally should be our last class, which is a good thing, right? So can someone just have us read the example that I gave you? It was a practice question, not so. Who did I give this question to? Okay, so I'm just going to dictate because I gave you this question. You don't need to write it. So it's for me and just trying to extract the data that I need to solve the question. All right. Okay, so we said the question sounds something like this. So a well is 0.3 meters in diameter. You don't need to write this. I think you already have this. Okay, but then we're just going to extract the data. All right. So what's coming out from there is that our diameter given is 0.3 meters. All right. And penetrates at 33 meters below the static water table. I think this can only be shown once we sketch something, not so. And like I always say, you always need, especially for this course, have a sketch. Whatever information is falling under that question, try to place it somewhere. You know, sometimes when we're marking, we just see how you're placing the values and the information. We can tell you know what you're doing, even if you make a mistake at some point. So it's just important that you do that. So it penetrates at 33 meters below static water table. After a long period of pumping at a rate of 30, so this is our discharge. So it's a 30 liters per second. The drawdown in wells 17 meters and 45 meters from the pumping well or the pumped well is found to be a 3.6 meters and a 2.2 meters. So from what I get from there is that, okay, let me just try to sketch it as well. So this looks like my pumped well, okay? 17 meters, there is an observation well. And then 45 meters from the pumped well, there is another observation well. So this can be looked at as observation wells. You just want to see the radius of influence. How much is your pumping affecting people next to you? Are we together? All right. So the basic information that has been given here is that the diameter of this information or pump is going to be what now? What will be the radius? What's the radius of the well? If the diameter has been given,
0.15.
we know where that is coming from, not so? because the formula does not allow us to use a diameter. We work with the radius. So already in your mind, you should have this value, okay? Then we move on. The pumped value, or discharge rather, they're saying is a 30 liters per second. You and I know that at the end of the day, we're working with SI units. So it's a meter per second, it's a cubic meter per second. So work with this liter and make it in the right units. So 30 over a second, if I'm going to divide this by 1,000, because it's a conversion factor, I'm going to get a what? 0.03 cubic meters per what? Per second. That's one part. They also talked about this wall penetrating the water table 33 meters below. So if this is your surface, just try to imagine that this is your water table, your original water table before you pump out water, all right? So meaning 33 meters below, let me assume it's somewhere here. And just from the question alone, you should be able to tell that this is what? A confined or unconfined? It's unconfined, right? So you can safely say this is your aquiclude or your aquitard, but this is where the aquifer ends, okay? So your well penetrates 33 meters below the water table. This is our water table, meaning the whole lot of this space is 33 meters. Are we together? So we're getting information from the question to have a sketch. This really helps us understand what we'll be doing. I'm not happy with this drawing. Tuwa mwana wachina olwaliri insona yoy. I can really bring it here. Nope. Okay. Generations to come will be watching this video. So if we fade Monica, Otawe basata bare mbere bwino paria. He's an old man now. Okay, so 33 meters below the water table. So this is your water table, this is your surface. Are we together? Then they are telling us the two observation wells. They haven't mentioned these are observation wells, but observation. Sometimes they're known as test wells. So they exist, you can say 17 meters away. So one is 17 meters. Then the other one is 45. Meters away. From the information, there is a respectively there. So they're saying that from the pump well, this is a pump well, by the way, where the discharge is. 17 meters away, there's a drawdown of how much? 3 point what? 3.6 meters. So a drawdown is, if this is your original water level, the more you pump out water, what happens? It draws down. That's just what it means when we say draw down. So if this is the original water level, the drawdown in an observation well, which is 17 meters away, is showing that we have a 3.6 meters drawdown. So from here, it has dropped. But then I'll get back to the water table and what happens to it, okay? The observation well, which is 45 meters away, has got a drawdown, which is fairly smaller, 2 point what? What this means, like I said, when you begin to pump your water out of your aquifer, you do not expect the water levels there to remain the same. They will draw down. So if they are drawing down, they are also affecting your neighbors. So if this is your neighbor's borehole, the water levels are also what? They're dropping. So if you're going to drop, let's say I'm somewhere here, this is where my water levels are after pumping up, for 24 hours. What this happens, or what this means, is that even the water table on the observation wall also drops. So you can safely say that this guy is coming from somewhere, and then he's found this drawdown here, and then maybe we can safely say this is where this drawdown is here. So originally this is your water table, but after pumping for 24 hours, what happens? It drops, but then when it drops in your pumped well, you don't expect this water level to just remain the way it is. So it also sort of sags. Last time when we met, we talked about a radius of influence. Do you remember that? Are we okay so far? We are. Now I'm seeing a lot of, I am not too sure where that is coming from. Ask. Yes, madam.
Me, I'm just close to how you feel that this one is a confined zone. Depending on how your pumping.
No, from the question, you remember we only have two formulas. One has got a depth. Huh? Is it called a depth? Or the thickness. If that hasn't been mentioned, then that's it. Okay? Mostly, if that hasn't been mentioned, then that's about it. Do we understand what is happening here? So originally, this is our water table, but the more we were pumping out water in a day, we expect the water levels here to just drop. And if these water levels here are dropping, it is not sparing our neighbors. So our neighbors could be these two guys. So this is where the line is sagging. It's a cone of depression, a radius of influence. It means that even on the other side, it's happening. But we just try to concentrate on one part just for academic purposes. Are we together? Okay. If we have this, then we are practically done, because we can find this height. We can equally find this height, which really comes in very importantly in our calculations. The value of K is sitting somewhere around there. We discussed what a K was, not so. Okay? Just a hydraulic conduct is just the rate at which this soil is allowing water to pass through it. So, from our discussions and our diagrams, this means that this is your height of the well, not so. So you leave it there. So the question wanted us to find, one, the hydraulic conductivity, which is the K. Then two, it wants us to find the drawdown. The drawdown, I'm going to say this for the last time, is just the movement of water from its original position to wherever it is now. This is your drawdown. But then you can't find the drawdown if you don't have the height of the well. Don't find guys. So we can just label this draw DD, drawdown. And then we'll come back to this later on. Cool. What's the formula for finding the value of K? K is equal to what? We said R1, R over H. Is this formula okay? So we're not using one with the depth, right? Because this is a very unconfined, and that's the formula for the unconfined. Let me just put it here. So unconfined So now notice this. The K, that's the question mark, right? Are we together? The K is a question mark, and that's what we're looking for. The R1, well, we can maybe say 17 is our radius of influence. R of the well, we can say we have the 0.15, right? When we come down, the pi is already a constant. H1 is just a distance, because this is where our reference point is. So we're going to be interested in what this value is. But then the height of the well is equally what? A question mark. So if we're going to consider the well as the radius of the well there in that formula, it won't work. Because this guy is unknown, this guy is unknown. But there's a different way you can go around this, okay? So instead of making this the pumping well, you make the distance from here to 17 as the pumping well. Can I repeat that? Instead of making this radius of the well as the pumping well, because it's not working, clearly because there's a value missing and the K is also missing, you now have to take the distance from the middle of the pumping well to 17 as your radius of the well. No, RW. R1 will have to be the bigger one. Also notice that your R1, your H1, these are bigger values than their colleagues, so to speak. Are we together? So instead of having this as a 0.15 radius, you're going to get your 17 as your radius of the well, and then the 45 as the R1. Everything okay? And I thought I gave you this question to try out. Who found some answers? Unapeza cha? You see, that's why he's very attentive, because he tried. Usually how education works, if you really want to, what's the word I'm looking for? Assimilate, understand, become a sponge, go through what you'll be learning. If a lecturer touches on that part, it's very easy for you to relate. Oh, I got stuck there. I never understood. Or I solved, I got stuck here. Let's see how he's going to go about it. If you go through that process, it's very easy for you to just remember stuff. It will be hard for you to not remember. So, nobody solved this question. What did you find? 4K, yes.
0.0001.
Okay, that sounds okay. The same with you? Same name, eh? Look, if you didn't do the question, find time to go do it, but then take advantage of what we're doing here. It may just come in an exam. Are we together on how we're going to proceed from there? We cannot make use of the HW because it's a question mark. Neither is, the K is also a question mark. So it won't just work. So what you revert to doing is, get your 17 as your RW. Get your 45 as your R1. From there you find yourself a K. When you find a K, get it back into the original equation, and then solve for HW, make the HW the subject, and then once you find this value, just come and subtract from what? Welcome to engineering. All right, so let's proceed. So, what I can do from here, just to not confuse people, I can say my K, some redefining the formula, right? I won't change so much. So the Q remains the same, ln remains the same. So let me do this. Let me say R 45 over R, are we together? Pi open brackets. We didn't do this. This is just a difference of 33. We subtracted 2.2, right? So what value is this? 30.75 meters. Remember, we don't need the drawdown in the equation. We need that distance from the base of your aquifer to where the drawdown is. So basically, we're just looking for the height of water. So if we already know this is a 33, we subtract these bits and then we get that value. We can equally do the same here. What's the difference? 33, we subtracted 3.6. How much? 0.5. 0.45.
9.4.
Or just 4. Okay, so even here I can say H. Okay, let me still maintain the 45. 45. I'm raising this to the power 2 minus H 17 raised to the power 2. So I have sort of designed the formula. Instead of making use of the well, and I'm not using it because it's got a very unknown value which can't work with another unknown value which is K. So I'm going to take the 17 as the rate. So it takes up the place. Once you do this, your K then should be a 0.03. Lean, the radius of 45 is just 45, right? So 45 divided by 17, we close. Everything being divided by a pi. Open bracket. H 45, which is 30.75, raise the power 2. Make sure to put the brackets there when you're punching. And then we have a 29.4, raise the power 2. If your mathematics is correct, let me see what I had found here. Okay, so this is like a, let me say 1.14 by 10 raised to the power negative 4 meters per second. If you don't want to leave it in that format, you can leave it in this format, which is much easier because you're going to be making use of it. 114 meters per second. So that's your conductivity, your hydraulic conductivity. So now we know this guy. So we know the value of K, and we understand the value of K as just the rate at which those soils are letting water pass through them. Are we together? And since these soils are assumed to be spreading everywhere, we can now make use of the value of K to go back and find the value of HW. Yes? Okay, so that's your first answer there. I want to erase this. Let me try to work from here. So once you find the value of K, then you have the right to go back to the original formula. Okay, so now you can say our K is equal to Q lean open bracket R1, R of the well, H1, H well, and then it ends there, right? So we have the K now, we have the discharge, we have all these values. We are just remaining with the HW, which is what we're trying to do. So now, because we are good mathematicians and we don't need to go through a step-by-step process of making HW the subject, we can just write it I. Or we can try to do this. Just a quick one. I hope I don't take too much space here. So Q R1 RW is equal to a K pi H12 K pi HW2. Is this okay? And then we're trying to make this a subject. So I can say HW is equal to, so my K pi H1 raised to the power 2 minus a Q ln open bracket 1 over that. We're going to divide this over a K pi, and then because the 2 has to be here, we just square it. Huh? So this is what we'll be working with. Okay? So we're looking for the HW. Once we find the HW, we come and subtract. We find ourselves our drawdown. I'm just going to place the values here. So the K we said is 0.00114 by, so which H1 or R1 do you get? It doesn't matter. Are we together? Your R1 could be a 17, your R1 could also be a 45. I haven't tried this in a long time, but when I was a student, I tried it and the answers are just the same. So the one that you pick as your R1 should just correspond or work with what your H1 is as well. If you're going with a 17 as your R1, then your H1 should be a 29 also. If you're picking up a 45 as your R1, then your 30.75 is your H1. Yes? So you can try at your own time, work with 17, work with 45, but to reduce the margin of error, I just work with the 17. So what's the H1 for if I'm going with the 17? 29.4. Remember to raise this to the power 2. Discharge is a 0.3. Lane, if I'm working with a 17, the 17 sits here. What's my RW? You will need to really be sober when you're doing this, because once you miss it here, then everything is wrong. Understand the question. The question said a diameter, right? Tomorrow, depending on which side I'm waking up from, as I'm preparing the exam, I'll say that's the same radius as 0.3. You exercise now on a diameter. In the exam, it was a radius. I've had sleepless nights over some mistakes I used to make when I was a student. Okay? So our 0.00114 by a pi. Okay, we ate into this space. So if your math is correct, what did you find as your HW? How much? 21.65. Yeah, this brother has been accurate. Okay, so your HW is a 21.64 meters. So this is just how much water is left in HW. Yes, sir? I've missed the pi? You mean like writing it? Oh yes, thank you. So pi, okay, thank you for that. But if you punch this well, I remember this guy coming to the office, okay? So I was trying to wrap around his head around how do we go around this. But I only came in because I had seen some effort from him. And usually that's the best way you learn. You can't just come to me and say, how do you solve this? Show me what you have first, yeah? So your HW is a 21.64, but it's just this. The question said find the drawdown. Drawdown is the distance literally from the original water level to where we are now. So your drawdown, so therefore your draw down is just a 33 minus a 21.64. This should give you about an 11.6. Go and confirm these values and figures in your room. I could have made a mistake, he could have as well. Chances are very minimal. But this is how you solve this question. Ideally, this is the extreme of this topic we can ever find. But then from here, again, I know the question didn't say, you can equally be asked to find the transmissivity. We talked about that, not so? Yes. How did we define transmissivity? What was the formula? Transmissivity is equal to what? K by... Okay, it doesn't really matter. But then in this case, the K already know what it is, not so? Yes. What is our B? What is our B? Yep. These are questions you only see maybe in my exam. So if you find it here, find time to just understand it. Okay, so the whole lot of this is your B. So why some of you were saying B is because in other materials, they have used B to cater for both the confined and the unconfined. This one covers both. But the one that is just a T, K, and then there's a D here, this one is just mostly for the confined. But the principle is just the same. You are just interested in the aquifer, the depth of the aquifer you're considering. So you can have 3 questions from this. Transmissivity. So that's how we find it. That's how we find the values that we're looking for. K is everywhere. So the drawdown is an 11.36. Again, we are engineers as of now. This shouldn't shock us that your HW, much as the drawing is comparatively smaller, but the value is bigger. This is just a sketch. Huh? It's not drawn to scale. You don't expect this to be 17 and then this to be 45. It's just for illustrations. Yes, sir? Mm-hmm. Yeah, so when we go back to the original equation, the R1 is any observation well, or it is an observation well which is further away from the pumped well. Not so. But in this case, Tina really. So which one do you pick? So any, it's up to you. The answer should ideally be the same. And find time to do this at your own time. So if we decide, like we did, to make use of a 17, are you getting me? So if your R1, you decide to be a 17, then you're getting this as your H1. And that's what's happening there. But at your own time, if you decide to make 45 as your R1, then make the 30 here as your H1. Yes, madam.
Just a repetition on what you said.
I repeat? Okay, so the T, transmissivity, right? K is just the hydraulic conductivity. The B is just the depth of your aquifer. It's just the depth of your aquifer you're considering. And in this case, this is the aquifer of interest to us, which is 33 meters. And I say that some materials, they use a B so that it caters for both confined and the unconfined. And then others use a D just to be more specific that we're dealing with a very confined aquifer.
So basically, it's just K times HQ.
Yes. And what will be the units here? What are the units for T? Yeah. So it's area per second. Yeah. It wasn't in the question originally, but I was just thinking beyond what we have. So we have one more topic, which I'm very much able to leave in your capable hands, that you're going to study and understand it. It's got nothing to do with calculations, but you just understanding what is going on. If you don't fully understand it, you can always approach not me. You're free if I'm around, okay? But that's basically about it for hydrology as well. If there are any questions, we can talk now. We have tests next week, right? You haven't gotten back to me, madam? With the times and the dates. I think it was a Monday we agreed, right? Who's saying no? I may be out of town by Tuesday, so Monday is the only day that I have to be here. And you guys need your own CAs. So, Monday we'll write one paper, and then Tuesday we'll write the other paper. 1 hour, 30 minutes, max for each paper. So it's your mandate to just find me that space where we can come and talk. All right, any questions? Topics? It's wells. Just wells. Could be hand-dug wells, it could be any type of a well, but the module actually has all the information. It's just about you reading more about it. But I'm going to send you something through the classroom just to guide you on the topic and the subunits I would want you to concentrate on. Nice chap. All right, chapwa. So see you on Monday. Madam, get back to me with time and inform everybody. Yes, sir. Someone is asking a question. Okay, so what I meant to say was for this question, they gave 0.3 as the diameter. So you need to pay attention because in your test or exam, I can still maintain the 0.3, but as a radius. So you need to know what works for your formula and how do you get it from there. So for this question, diameter was 0.3. That's why we're ending up here as a radius. But if a question says your radius is 0.3, then you still maintain the 0.3 that was there. Just pay attention. All right, guys, so we'll see you on Monday. Sabam Putei.